Okay, thank you for coming back. Let's continue this workshop of light-based quantum technologies. And I will introduce the first speaker of this afternoon. So it's Dr. Adriana Lita that came from us all the way from Boulder in the United States. Adriana is a pioneer in the development of technologies to detect one photon at a time. She's been first working on material science. I mean, if you want, you will see that to detect single photons, you need excellent superconducting materials. And so she's first been working on these superconducting materials and then progressively developed very important technologies that are, I think nobody would believe that we would reach this kind of efficiencies now, today. So you can detect photons with efficiencies. I won't give the number because I'm sure I'm not up to date, but very close to 100% now. And you can even tell if an electromagnetic field embeds 1 or 2 or 3 photons. So this is, as you can imagine, absolutely critical enabling technologies for quantum technologies based on light. So her work has covered many applications. It's not only about developing these detectors, but it's also integrating them in different systems. And as we'll see during our talk, it gives access to a large range of applications. I'm very, very happy that this workshop gave me the opportunity to meet Professor Lita. You will see we have a fantastic speaker. Thank you. Let's welcome her.
Good afternoon. It's an honor to be here. Thank you, Pascale, for inviting me. Today I will be talking about an enabling technology for quantum information applications, and single-photon detectors along with single-photon sources are enabling quantum information. So I will start by talking a little bit about the history of the field for the superconducting single-photon detectors, and how we optimize them, and also show some representative applications. So let me just start with the definition. A single photon detector is a device that is able to produce a measurable output signal distinguishable from noise due to a single photon. I have to say that I will be focusing on this region of the electromagnetic spectrum here, and the devices that I'm going to show you are optimized for telecom wavelength, lambda 1550 nanometer, so the energy is on the order of 10 to minus 19 joules. We're measuring these energies. Let me start by putting this list of what are the performance metrics that are important for single photon detector for quantum information applications. So system detection efficiency, and of course this is crucial for minimizing losses in long distance communication. So we'd like to be close to 100%, as close as possible to 100%. The ability to distinguish between one and multiple photons is essential for advanced protocols. So energy resolution, or for a monochromatic beam photon number resolution, is important. Also, low jitter ensures precise photon arrival times. Recovery times of the detector allow you to count at really high rates. Of course, this detector counts single photons, so we would like the dark count rate or the background count rate in some detectors to be as close to 0 as possible. And if you're able to tune the wavelength for different experiments, that would be great. And there's other considerations such as operating temperature, have to do with cost, and scalability. So let me just go quickly through this, all of these parameters to see what I'm talking about. For example, for system detection efficiency, the system detection efficiency represents the fraction of photons that have been already coupled into an optical fiber and yield a measurable electrical output. So I'm not looking at the efficiency in which you couple into the fiber, but how the detectors are actually efficient. And this has a few components. It's the efficiency to which you couple from the fiber to the detector the photons. There's also the quantum efficiency that includes the absorption absorption in the detectors. Here I'm showing a TES, a transition edge sensor in a cryostat. And you have a fiber that's coupled to it. And so it's the absorption in the TES and also the intrinsic efficiency, which has to do with once the photon is absorbed, what is the efficiency, what is the probability that the detector will input a signal. And then the trigger efficiency, which has to do with the probability that the readout electronics are able to pick up that signal. So photon-number-resolving, depicting here, when the output signal is proportional to the photon number, then you have a photon-number-resolving detector, and a conventional click detector would not be able to distinguish between different numbers of photons. Now, timing jitter, it's the uncertainty in determining the photon arrival time. So when a photon arrives at the detector, there's some time until the electrical pulse exits the detector. This is called detector latency. And there is some variation in the detector latency, which basically is the timing jitter. And this depends on the rise time, pulse size, amplitude noise, bandwidth of the electronics. Recovery time, the way we simply define it, is that the time it takes the detector to be ready to count the next event. So there is some dead time in which the detector, after it detects one photon, is not able to detect. And then there's a reset time in which it goes back to the initial efficiency. So that is actually the recovery time. You can have some detectors in which actually there is no dead time, like the transition edge sensor. As you will see, it's measuring energy, it's a calorimeter. However, if a photon comes too close to the first one, then you can have pileup, and it's hard to distinguish. And so we define this as 1/E time constant of the recovery for the number of the recovery. Now, dark counts are counts registered by a detector when all input light is blocked. And these are false registering triggered by electrical or thermal fluctuations. And they can be due to tunneling effects after pulsing. There could be material defects. In the case of superconducting detector, you can have cosmic rays energy deposition. They are sensitive to that. Ambient radioactivity and maybe quantum fluctuation. So it's been demonstrated that for superconducting single photon detectors, you can have less than one count per day of dark counts. Background counts are counts that are registered by a detector when all input light, when you have a fiber connected to your detector, so you could have photons from black body radiation from room temperature objects that propagate down into the optical fiber, creating a background count rate, and you can also have some external light coupled. And here I'm showing a plot where the three peaks that you see here are counts from a pulsed 1550 laser counted by a transition edge sensor. And when the laser is off and the end of the fiber at room temperature is connected to a different temperature from 0 to 70, you can see this increase in the black body radiation that the detector can count, and it overlaps with one photon signal from 1550. Let me start by talking the oldest single photon detector technology, which is the photomultiplier tube. And here it works on the photoelectric principles. So the photocathode, when a photon is impinged on it, converts the photon to photoelectrons. And it contains a series of diodes that are each at higher positive potential than the last. So then you create this signal amplification through multiplication of secondary electrons. They work best in UV and blue. You can see here wavelength and the efficiency of the PMT based on different coatings for the diodes. And here I'm putting in this table all the parameters that characterize the PMTs. So their efficiency is about 40%, or it could be lower, and they do have energy resolution also. They have really nice timing properties. So the recovery time is 50 nanoseconds, timing jitter 50 picoseconds, and the dark count can be as low as 200 counts per second. Their operating temperature is room temperature, so that's really a nice thing, and they have really large area. So the PMTs are used very much today in spectrophotometer, medical diagnosis, LiDAR, and high energy physics. I want to also bring up the single-photon avalanche photodiode, the SPAD. So these are the workhorses that every quantum optics lab has in their lab, and this works on the principle of reverse bias, a PN junction above its breakdown voltage, and a single photon-generated electron-hole pair can trigger an exponential growth in current through runaway impact on ionization. So there's been a lot of optimization, and you can see that you can have thin silicon SPADs that have really low jitter, tens of picoseconds, and lower detection efficiency. There's thick SPADs that you have higher detection efficiency, so there's a trade-off between speed and also detection efficiency. And if I also compare here all the parameters that describes the SPAD, you can see that the efficiency can be as high as 85% in visible with silicon SPADs. It's a bit lower for InGaAs, and you can have some energy resolution with arrays. Recovery times and timing jitter are really nice, and dark counts can be as low as 100 counts per second. They also operate at room temperature, so that's another advantage of SPADs. And there's a large number of applications, as everybody knows, that from quantum computing, QKD, 3D imaging, biomedical imaging. So now let me switch to superconducting single-photon detectors. And superconductivity is a distinct thermodynamic phase observed only in some solids. Exists only when temperature, external magnetic field, and current density carried by the material are below some critical values. And in the ground state, the superconducting ground state, the electrons are bounded together in the so-called Cooper pairs. And the excited state, they are no longer bounded, but they are called quasi-particles. And there's an energy gap on the order of the superconducting transition temperature, which is really low, milli-eV. And here I'm showing a material that shows this transition from normal resistance to zero resistance, and the transition is on the order of 12.5. And also here a device where you can have zero resistance by increasing the current until you reach a critical current where it snaps, and you have a voltage appearing here due to exceeding the critical current or critical current density in the device. There's two types of superconducting materials. Type 1, where it's a perfect diamagnetic material, where below a critical magnetic field you have a superconductor. There's also type 2, where you can have a mixture of normal and superconducting materials, where is energetically favorable to have the field penetrate the material and create these vortices. Now, superconductivity allows us to observe macroscopic quantum effects, specifically tunneling and energy quantization, as flux quantization is shown here in a superconducting ring. And this can exist in macroscopic man-made electrical circuits. These are, they could be qubits or superconducting quantum interference devices. So the sharp transition that I mentioned earlier have been exploited for superconducting single-photon devices, such as transition edge sensor and also SNSPD, or superconducting nanowire single-photon detector, which I will be go in more details. Now, why superconducting detector? Well, if you just compare the energy bands here, you can see that if the photon has the energy close to the energy band in silicon, then you would have just one electron hole pair that it's generated in a semiconductor material. However, for a superconducting material, because the energy gap is so small, you can have hundreds to thousands of quasi-particles, so much higher sensitivity. And they do require cryogenic operation, but the reason they do is because you have the lowest noise. So what is transition edge sensor? It operates on the calorimetric principle and turns photon energy into heat and measures that. You have an absorber where the energy is deposited from a single photon close to a contact to a thermometer. And also the absorber is connected to through a weak thermal link to a thermal sink. The thermometer is an exquisite thermometer that can measure single photon detectors, and it's actually the superconducting transition in the material. So the sharper this transition, the more sensitive your detector is. So alpha is a parameter that characterizes this property of materials. So you can have a really small change in temperature from the energy of one photon, and then that gives rise to a measurable resistance. So the temperature change is proportional to the energy deposition. So this is a spectrometer, and the recovery time depends on the thermal conductance and allows the absorber to equilibrate to the thermal sink temperature. They operate to temperatures of around 100 millikelvin, and that's because we need to suppress thermal fluctuation noise. That's a fundamental noise that we need to keep really low, and because it depends on temperature and the heat capacity of the material, we make really small detectors very cold. So here are some examples of TES devices across the spectrum, and we have the cosmic microwave background arrays of TESs that study the physics of extremely early universe. You have terahertz imaging arrays that are used in making system for standoff security applications. And there's the single photon detectors that I will be talking more about, where you have you can also do optical fiber power measurements traceable to cryogenic standards. And of course, quantum information applications. There's the X-ray detectors, which are widely used in astronomy, and also gamma ray detectors that are used for nuclear non-destructive analysis. So in 1998, this paper came out and showed that you can use a transition edge sensor to count single photons in infrared, optical, and ultraviolet. This is a tungsten sensor and 18 micrometer on the side, and it was able to detect single photons from 0.3 eV up to about 3 eV. And interesting, the difference between the previous detector I showed is that the entire microcalorimeter is in the superconducting film. So both thermometer and absorber are electron in tungsten, and the weak thermal link is actually the decoupling between the temperatures of electron and phonons, and the thermal sinks are the phonons in tungsten. So we used an electrical circuit to measure the temperature change. And the TES is shown here as a variable resistor. It is voltage bias. And the voltage bias keeps the electron in superconducting to normal transition via Joule heating. When a photon is absorbed, then you get an increase in the temperature and then resistance. And you also, the heat in excess of Joule heating is removed through a drop in the Joule power dissipation. So basically you get this drop in current, and the area under the pulse here is actually exactly enables direct measurement of photon energy, is the integral of current change times the voltage bias. So here's this is the output signal of the TES. You have proportional signal to incoming photon energy. It enables direct measurements of absorbed energy. You have rise time on the order 100 of nanoseconds and pulse duration 1 to 2 microseconds. So these are slower than previous devices. Essentially, they have no dead time. As I mentioned, you would be able to detect the photons, which comes after the first one, but then it could be piles pile up, and you need to do some post-processing analysis. Some of the materials that TESs have been done are tungsten, titanium, hafnium, some bilayers. This is one of the first papers that put the transition edge sensors on the map for quantum applications. And this shows, the plot here shows a direct measurement of the number of photons in a single pulse of light. This is only a 20% efficient detector, and it also showed the Poisson distribution that is expected from this pulse overlaid with the measured signal. The same detector actually showed the direct observation of the quantum interference phenomenon. So when you have two indistinguishable photons incident on the beam splitter, they would both go together either in one arm of the interferometer or the second one. And this is depicted here. You can see the probability to get two photons in either B or A detector is maximized when you have no time differences between the arrival times of the two detectors, and also the probability to get one in the other detector is close to zero. So this is only a 20% efficient detector, so the next step for us was to optimize the efficiency. And the way we did that was, first of all, these are about 20 micrometer squares devices, and the coupling absorption needed to be improved. So we did micromachining of devices with this lollipop shape, and this allows us to do this self-alignment in which the center of the fiber ferrule where the light comes in is perfectly aligned with the device chip. So these are all commercial components that we are using, and this enabled us to get less than 1% error in our coupling efficiency. And then the next step was to make this tungsten film higher absorption. Generally in the region of interest here, wavelengths from 1,000 to 2,000 nanometers, you get about 35% efficiency, and by embedding in an optical stack, you have a mirror underneath, you have some non-absorbing dielectrics, then you can increase it to close to 100%, and that's a measurement of a system detection efficiency at 1550 and the measurement of the absorption in the film from which we made the device. So several groups have shown that we can do now above 98% 1550 nanometer detection efficiency. And so once these detectors became really efficient, then they were used in this loophole-free Bell test, which ruled out the local realism in 2015. This was a landmark experiment, and it took 50 years to close all the loopholes because it has been technologically challenging and requires spatially distributed entanglement, unpredictable measurement settings, and really high efficient detectors. And so three groups have done the experiment in the same time. The first one used matter qubits, and the second two ones used the photonic qubits, and they used tungsten optical TES and SNSPD, really high efficiency devices. So this is what makes TES different than other single-photon detector, the intrinsic ability to resolve energy or photon number. One way to characterize that is to look at the full width half maximum of the statistical curve for one single energy for one photon. And here you can see that we have, for example, this device has an energy resolution of 0.26 eV. Here I'm showing another example where you can see that the nice separation is no longer here for higher photon number than 4. So above a certain photon energy, TES is no longer operating in the linear regime. And you can ask yourself how high a photon number is distinguishable with a TES, or how accurately can we distinguish photon numbers. Well, it depends on the photon energy and also the saturation energy. So we can design devices that saturate at higher or lower energy, depending on what the experiment needs. And also, we need to make sure that the photon number peak separation is large enough, so we keep the error down. So here is an example where you can extend the photon number resolution beyond linear operation of the regime. You can see here that above about 12 photons, this device is no longer in the linear regime, and it still is able to distinguish really nicely photons. This is another example where also you can't see really with your eyes the photon number resolution, but when you look at the full waveform of the pulse, then you can actually get more information and distinguish the photon. You can have a much better photon number assignment. In this case is for photons less than 10, photon number less than 10, you get a probability of correct assignment larger than 99%. And one other way to look at this is how can we push the limit of energy resolution. And one of the processes that we looked at is how can we recover some of the athermal phonons that are created in the first stages when a phonon is interacting with the detector. It creates this hot electron plasma, and then in this stage there are a lot of phonons with high energy that are emitted, and they escape before they are measured. So that actually degrades our energy resolution. So some things that we can do are fabrication of the devices on membranes, which allow escape phonons to be recollected, and also maybe use acoustically mismatched substrates to block these high energy phonons to escape the detector material. So here's an example of a record energy resolution at 1550. I want to draw your attention to the y-axis here. This is a log scale, and you can see how well we can distinguish between different photon numbers. This is 40 millieV at 1550. But the trade-off is the fact that this has a longer device recovery time. So we can also optimize speed. Our devices are limited by the weak thermal link between the electron and phonon in tungsten. And one way to overcome that is to provide thermal link engineering in which you give another path to the heat through these gold fins that we place on our devices. And this way we demonstrated counting at 1 megahertz count rates with our detector and still keeping really nice energy resolution. One application that really benefited from really high efficiency, low noise, and good photon number resolution is photonic quantum computing. So you can encode the information in a continuous variable, such as the amplitude or phase of a non-classical light state. And I think this was already introduced by Professor Silberhorn, but basically you can use Gaussian boson sampling system here to generate qubit states, and what the PNR detectors do, they actually are heralding qubit states at the remaining output modes of the GBS device. This is a paper that showed that photonic quantum advantage can be achieved with in all gates programmable by Xanadu. They have demonstrated scalable generation of GKP states, and some of the details that went into the PNR detectors are the fact that their efficiency are really high. They actually showed here 99% efficiency for TES detector, and they were looking at photon numbers 7 and also really nice distinguishability between photon states. So I want to switch now gears and move to the other superconducting technology that our group works on. These are nanowire single-photon detectors, SNSPD. And they generally are a really thin superconducting film patterned in this narrow wire, maybe 100 nanometers show here, and meander back and forth, or it could be just one wire to study some fundamental physics problem in the device. In 2001, this paper came out, and it showed that it is possible to detect single photon in a 30 picosecond time frame. This was really fast, and although this device efficiency was really low at the time, it was just a single wire that caught the attention of a lot of people, and it is 2026, 25 years later, you're going to see a huge difference. There are lots of companies who are now commercializing the SNSPD, so there's a lot of work that has been put into optimizing these devices. But what's the operating principle? So you have a narrow strip of superconducting material, very thin. It is biased really close to critical current. When a photon hits, it creates a hotspot, it breaks the superconductivity there, and the current is actually diverted around, and at one point it will exceed the current density. It's going to go above the critical, and then you're going to have a normal region across the wire, and at that time the current is going to be, the bias current is diverted into a load resistor, and you get a pulse out. Now, these are very fast, just like a switch. As soon as the superconductivity is broken, the SNSPD, which is shown here as a switch, becomes a resistor as soon as it becomes normal, and then you have this is in series with this inductance, because this long nanowire superconducting material has high kinetic inductance, and then the bias current is diverted in the amplifier. The rise time is on the order of less than 100 picoseconds, pulse duration 1 to 100 nanoseconds. This has a truly digital detection mechanism and reduced drift and zero read noise. Initially, they had no energy resolution, and the operating temperature is 1 to 4 Kelvin in most cases. So this is what you would see when you are trying to characterize these devices. You increase the bias current until you start seeing counts, and at one point, at a certain cutoff current, you start increasing the number of counts, and you see a plateau of saturating internal efficiency region. This is where you want to operate, because that's also where you have really low dark counts. There's a lot of materials that people have looked into. The more notable one are the amorphous material, tungsten silicide, molybdenum. These were the easiest to optimize initially. They've shown the highest energy, the highest efficiency. And then the polycrystalline materials, which are higher superconducting transition temperature, they've had some issues with optimization of the fabrication, but now are almost at the same level. I want to also mention that single photon detection at 1550 has been shown in MGB2 at 20 Kelvin, and this is incredible. This is also a hard material to work with because water degrades superconductivity in MGB2. Hopefully there's ways to produce more of those detectors. Now, in terms of the system detection efficiency, we use the same ideas as we apply for the TES. We increased the coupling using the same self-alignment technique. And then this is where the nanowire is. We use a mirror again. In this case, is a dielectric stack of I think 13 layers, and then on top there's an AR coating. So this is showing here in 2020. This paper has shown that yes, for even for nanowire detectors, you can get close to 100%. This is shown 98% when you optimize for the maximum polarization. So a few papers have demonstrated that now they can make more than 98% efficient detectors. Now, let me talk a little bit about the speed. So the rise time of the detector depends on the kinetic inductance and the resistance of the hotspot. Also, the fall time here depends on the kinetic inductance and the readout, which is generally 50 ohms. So since the kinetic inductance is proportional to the length of the nanowire, larger detectors will have longer dead time or degraded timing jitter. Here again, for slower slew rate, you get degraded jitter. So you get these red curves here. And that corresponds to larger inductance or larger area detectors. So in order to study the what is the best jitter that we can get out of these devices? This experiment here used a short nanowire, 5 micrometers long and 100 nanometer wide, and showed that you can actually get timings record of 4 picosecond jitter at 1550 nanometers. There's though a trade-off, right? When you want high efficiency, you need to meander this wire back and forth so you can cover a larger area that overlaps with the pulse mode, the light mode. So if you want a fast detector, then you probably need to come up with other ways of improving both efficiency and jitter. So this is a paper that showed the record in SNSPD speed. Here, this group at JPL has shown that you can maximize the count rate when you use an array of multiple interleaved meanders in a parallel readout. And this is showing the optical, the sampling with the array of an optical fiber mode, the SMF28. So this detector has 78% efficiency, timing jitter less than 50 picoseconds, and a count rate of 1.5 gigacounts per second. This is one application that can benefit from using these detectors, and this is quantum certified random number generation. In this paper, the researchers at NIST have used the Bell experiment, and they generated random numbers by using the same setup. Because the measurements satisfy the conditions of a Bell test, the resulting bits are proven to be fundamentally random by quantum mechanics. And here's an interesting plot that shows the time it takes to produce 512 bits of quantum certified random numbers in 2015 was about a day. That was for about less than 75% system efficiency. When we got above 80% system efficiency, that it's around 20 seconds. So in this experiment, the photon pair rate is kept low. So a PNR detector would actually benefit this experiment because it would limit the double pair generation, and also faster detector would make higher source rates. So now I want to switch to talk a little bit about this really new area of photon number resolution in SNSPDs. So you can have quasi-photon number resolution when you spatially multiplex these threshold detectors. And here it's, this paper shows 28 nanowires are interleaved here in a parallel architecture, and you can have this fast discrimination up to 8 photons. They show the photon efficiency, one photon efficiency at 88%, timing jitter 80 picosecond, and speed of 200 megacounts per second. But even more interesting is the fact that you can actually discriminate photon number by looking at the pulse rising edge and amplitude. That contains information of PNR information, and this paper here have nicely shown that that is all, this information is all encoded in the timing jitter of the detector. And here this paper from Paderborn University has shown that you can unambiguously discriminate between 1 and 2 photon events. So this is one applications that can benefit from this type of detectors, quantum networking. So here I'm showing a quantum communication protocol that entangles 2 independent photons, these 2 red photons, that have never interacted, using only optical components and measurements. You see here like 4 heralding detectors and the measurement detectors. So this scheme requires precise synchronization between pulses, and so the timing jitter is a major limitation for distributing entangled photons. And so this would be the requirements to have a very successful entanglement, path entanglement swapping. So we want really high efficiency detector, as high at above 98%, really fast, to be able to distinguish between 1 and 2 photons, and also maybe 20 picosecond jitter, so really low. So where are we now? This is the paper that I showed with the highest efficiency, 98%. We can also make really a good timing resolution detectors. That was the paper that now it's also being able to distinguish between 1 and 2 photons unambiguously. And this is the paper that showed really high rates. So we can do this in separate detectors. The goal is to put all of them in one, and that's not an easy work, but that's probably going to happen. And if you wonder where the TESs are, that's where they are. They're a bit slow, but they have really nice photon number resolution. This is my last technical slide. So the SNSPD, normally you think of them, they're narrow wire. Well, there's a paper on the archive that shows that these devices, this is the first demonstration as an SNSPD can be 0.1 millimeter wide. And it actually shows saturation. And this is done by using a new technology in which you have this niobium superconducting rails. You apply a current that has some magnetic currents that basically affect the critical current in your device and allows you to get closer to the depairing current. This increased the plateau length by 40%, and the dark counts are reduced by 10 to the 10. So this could be a game changer in SNSPD technology. And if you are wondering how all devices compare with each other, the superconducting single photon detectors have the highest efficiency. They have the lowest dark counts, and the SNSPD are the fastest detectors with the best timing resolution. And yeah, they are not at room temperature, but they are good for quantum information applications, and this is where the overlap between TESs and SNSPDs. And I want to end by mentioning that Seiyun has been a pioneer in superconducting single photon detectors. He established our group at NIST back in 2000, early 2000. And he was one of the pioneers for superconducting quantum devices, and basically pushed the field in a manner that it was unprecedented. So, and that's the group at NIST and all our collaborators. Thank you so much for your attention.